Welcome to the Computational Fabrication Seminar. We have two speakers for today's session on architectural geometry. Professor Nico Pietroni will first give a motivational talk, and then Professor Caigui Jiang will give a deep dive talk. We will have a short Q&A session at the end of the two talks. Nico Pietroni is a senior lecturer at the University of Technology, Sydney. His research focuses on concepts and practical algorithms for creating and manipulating digital shape representation. Nico is especially interested in how geometry processing intersects with artistic modeling and digital fabrication. His primary goal is to push the boundaries of current industry production pipelines by exploiting the theoretical foundations in geometry processing. This includes mesh parameterization, surface abstraction, and global optimization applied to the entertainment industry, digital fabrication, and architectural geometry. Professor Nico's talk will be on engineering the imagination, computational design for architecture. The floor is yours, Nico.
Oh, thanks so much for the nice introduction. So let me share my screen. Okay, can you see my slides?
Yes.
I hope so. Okay, thanks so much for the nice introduction. So today I'm giving a short talk about architectural geometry and open problems and some of the things that we have done so far. So first of all, a bit about myself. I'm actually now at UTS Sydney, but I've been visiting postdoc at NYU. I worked at ATH. I collaborated a lot with many people in different universities, and I worked a lot into the Xi'an lab, where Mesh Lab has been developed. Maybe you know Mesh Lab. Okay, so in general, when you talk about digital fabrication, and you actually have to think about this pipeline, which is also implemented in the case of architectural geometry. So you have an artist that starts with a concept, and then the artist produces a digital model, but this model is not suitable for fabrication. So what happens is, like, you have to refine this model through some skilled engineer to produce the final physical object that can be fabricated and delivered to reality. And architectural shapes makes no exception. So what is computational design? So the idea is, like, the designer knows nothing about what you want to achieve, and you have not even like a clear vision of the shape, but you can actually explore the space of possible shapes and object you want to fabricate. And the artist only focus on the design, and in the background you have a computer program that take care of all the constraints and minimize objective function in order to make the shape fabricable. At the same time, you have a way to explore and navigate all the possible solutions. So in this case, you can actually reduce this gap from what you can achieve in reality, what you can create as a concept by using advanced geometry modeling processing tool, and also 3D modeling and shape optimization tool. So architectural geometry is one instance of this problem, and during this last decade, there was a lot of research in architectural geometry on how you can apply architectural geometry, architectural design, and computational design, and applied math and geometry processing to achieve some shape. So, for example, if you see some of these shapes that you see around, like this incredible surface mesh, they always, when you actually start from a given shape representation, you have to deal with some physical constraints to bring these things to reality. Or, for example, you may need to create also superstructure to ensure that the surface is self-supporting and enough robust to be safe, right? In other case, you want to get developable surface, and there are examples in the real world, and given because they are developable, they are much easier to realize. Or you can have some difficult panelization strategy. For example, you can have some panelization made of doubly curved panels or hexagonal patterns. And basically, the more the patterns become complex, usually the more it's expensive to create the mesh. So in general, architecture 4.0 requires tools to face some common problem that you have when you create some kind of structure. For example, how you panel a shape, given the fact that you have to cope with the constraints of the material of the paneling, how you can improve performance, and how you can deploy these things to reality. So some of the most interesting works are in grid shells. Grid shells are this kind of thin structures that covers wide space, which are very difficult to make them robust. Usually the people rely on triangles, but there is also some research and people who want to do like grid shells made of quad mesh, or for example, hexagonal mesh. So the problem is like when you have triangles, the shape is much more robust because every time you try to deform a triangle, you put in compression or in tension one of the bars, while this is not true for quads or other kind of shapes that you can shear it, for example. So how we can optimize a grid shell made of quads? So the idea that we came out a few years ago is like to using the same amount of material to tessellate and adapt the tessellation to the stress direction. So put more cell where there is more stress and elongate the cells along the stress direction. So this comes with an initial step where we estimate the distribution of the force and the anisotropy of the force on a continuous shell that represent the surface. And then we can actually tessellate adaptively the mesh, and we show that our approach, even with using the same amount of steel, it becomes create much more complex, much more resistant meshes because the material is more efficiently distributed. So this is other kind of example. Here you can see the buckling multiplier for different shapes that we increase even like twice the amount of buckling multiplied for other shapes. And the amount of steel that we use is the same for all of them. So yeah, and nice thing is like this algorithm we designed can work with any kind of possible tessellation. I invite you to see the papers for detail. But there is another way to construct very efficient shape. For example, tensegrity. You can see like in Brisbane here in Australia, there is this Kurilpa Bridge, which is a bridge designed by Arup that uses tensegrity. So tensegrity is a concept introduced by Kenneth Nelson in art, and the idea is like you have truss and ropes, and the truss carry compression, the rope carry tension, and when they are together, the structure becomes very, very robust and also efficient because all the loads is in compression and tension, so it becomes very strong. So, however, most of the tensegrity has been designed for standard shapes. So you have a procedural periodic like assembly of this tensegrity, and so was difficult to actually extend it to different kind of shapes, freeform shapes. And the other problem is like it's difficult to understand when a tensegrity is stable because you have so many possibilities that you can deform this shape in so many ways, so that in the end you need also to define a way to understand when a tensegrity is stable. That's an extra challenge. So this is a work we did a few years ago where we start with a shape and we sample a set of possible connectivity, and we decide which are the ropes and which are the trusses, and we use a form finding and the simplification algorithm to ensure stability based on position-based dynamics. And in the end, it was working very well. So we assembled like one installations, which is very, very robust. And you can see that you never have a join of two trusses touching each other. So we also, there is people working also on structural glass. So how you can create like panels of glass that can be structurally strong. And the idea is like glass can only carry compression because it carries tension, it can cracks. So in order to actually make the glass structural, in order to use the structural property of the glass, in this work, we optimized the set of cables passing on the surface and imposing like some sort of pre-tensioning such that the structure is all in tension and you don't have an extension, extension of the panel, so you can use it, the glass as a structural element. So, but you can also define other kind of structures to support the weight. So getting inspiration of these famous architects from Italy who actually designed these trusses for reinforced shells, we created this method that takes an input shape and then define a field over the shape optimized to support, to create a set of trusses. So we discretize the field and then we find the optimal size of these trusses in order to use as few materials as possible. So again, in this case, it's the same concept, going from continuous to discrete, right? And then optimizing these trusses at the end. And you can see here these experiments that for the same weight and the same amount of material, so the optimized one is more resistant with respect to the non-optimized one, even though the material is the same. So it doesn't deform, or it deforms much less. And you can apply this concept even for everyday shapes or pipes or whatever has to support a certain weight, or even architectural shape. So another kind of interesting research topic is like how you can create complex shape out of very cheap object, and that's really scale up to architecture. So we came up with these flex maps where we actually take a mesh, right, and we split into patches, and then each patches we embed a spiral pattern that becomes deformable and can get double curvature. And the idea is like we can vary and we can explore the different kind of spirals and then have different kind of elasticity and mechanical behavior. So you can use this also to create some kind of nice pavilion. So for the pavilion on the right, we actually won first prize at the competition, and that was until a few weeks ago exposed at the Venice Biennale, which is one of the most important events in architecture. So I want to show you also other challenging research topics, which are very, very interesting. So there's a lot of people that works in deployable structure. So the idea is like how we can make something small that you can deploy in a very fast way, and it's like cheap. So this is a very interesting paper from the Mark Pori's team, where they actually have this X shell. So there are these kind of structures that you can open and close, and they actually can optimize and simulate how these things behave. Very complex optimization, I have to say. They also worked on, the same team works also on fabrication on deployable structures. So they actually use these kind of patterns that when they're deployed, they becomes stable. And also there is people who works in inflatable structures, right? So the same concept is like how you can deploy some kind of shapes in a very fast way. And this is a very challenging and exciting research field. And for example, this year at SIGGRAPH, there's going to be this paper, which is an umbrella mesh, is called. And basically, they implemented this kind of mechanism where you can close and open a mesh. And in this case, you can see that there is a lot of complex geometric optimization to understand the kinematics of these kind of objects. So I want to tell you that it would be really interesting to me, like to explore the case of deployable structure, but in the case where you actually use cables and nets to create like very fast tensor structure that you can deploy fast and reliably. That will have a lot of application in the real world. And another challenging topics, which I think it's need a lot of research, is real-time control, because sometimes most of these algorithms, for example, that do like optimization, and they somehow take inspiration from topology optimization. I can see here I put like 2 papers. They are nice in terms of optimization results, but they are not controllable. They are not real time. So you actually push a button, you wait some time, an hour, and you get the result. So it will be really, even though there's a lot of people working, and right now there is not like results, but it would be nice to get something which is not even like the global optimal, but it can be like real time and controllable. So that concludes my short talk. I hope I didn't talk too much time, and I hope it was enough interesting.
Okay, thank you, Nico, for the inspiring talk. So next, we will have a deep dive talk, and our speaker is Professor Caigui Jiang. Caigui Jiang is a professor at Institute of Artificial Intelligence and Robotics of Xi'an Jiaotong University in China. Before that, he worked as a research scientist and postdoc at the Visual Computing Center of King Abdullah University of Science and Technology, ICSI, UC Berkeley, and the Max Planck Institute of Informatics. He obtained his PhD in 2016 from King Abdullah University of Science and Technology under the supervision of Professor Helmut Portman and Professor Peter Wonka. He received his bachelor and master degrees both from Xi'an Jiaotong University in 2008 and 2011, respectively. His research interests are in geometry modeling, geometry processing, architectural geometry, computer graphics, and computer vision. Professor Caigui Jiang's talk will be on geometry modeling from flat sheet material. So, Caigui, so now the floor is yours.
Okay, thank you very much for your nice introduction. Let me share the screen first. Okay. So today I'm very glad to present my work. I call it geometry modeling from flat sheet material. So this topic is a summary of my research in the past few years. So here is an outline of my presentation. I will first introduce the background and follow with 3 specific research within this topic. They are curve-pleated structures, free-form quad-based origami, and shape-morphing mechanical metamaterial. So behind these topics, there are 3 basic concepts you may know: origami, charigami, and developer surfaces. So first, let's look at origami. So origami is a Japanese word, means paper folding. It's a kind of very old art. So I think almost everybody has more or less some experience of playing papers. So here I show some examples of origami. So here are 2 bows, a swan, and a frog. So someone could make even more complex designs. So origami has a very old history. Here is the first known book that has a record of origami, which published more than 200 years ago. But the concept and the designing idea has been widely applied in the modern technology, such as the designing of solar panels for space exploration. So on the top left, you can find NASA's design for International Space Station. So on the upper left is Mars rover, and upright is Mars rover, and 2 other designs for the solar panels for a satellite below. So other than that, origami has also been used in the field of software robotics. So here is an example from Harvard University where origami is used to simulate muscle motions. The charigami is another concept, still a Japanese word, means paper cutting. So compared with origami, the difference is besides folding, cutting is allowed in the design of Karigami. So this means Karigami has more degree of freedom for geometry modeling. So the idea of Karigami has also been widely applied in the material science as shown on the left, and also applied in the art design, such on the right-hand side is a pop-up structure. So here are two more examples of Karigami. So after cutting a shape, the structure show more degree, show new material properties, and also rich variation of curvatures. So the right ones is an aesthetic structure expanded from a square to a circle. So the third concept is the developable surfaces. The developable surface is a smooth surface with zero Gaussian curvature. So it can be flattened onto a plane without any distortion, stretching, compression, or cutting. So the smooth developable surfaces can be divided into three categories: the general cylinder, general cones, and the tangent surface of a space curve. So flat sheet materials are the most common form of raw materials. Then developable surfaces is widely used in the manufacturing related modeling. It can be used in the field of architecture design and also the manufacturing of boats, clothes, shoes, and others. So origami, Karigami, and the developable surfaces are the main focus of my talk. So next, I will introduce a curve-pleated structure. I consider it as an origami-related and a developable surfaces-related work. So our work was motivated by discrete differential geometry and inspired by the curve folding art, such as shown here by Eric Demain and his father, Martin Demain. So here the curve-pleated structure is a kind of origami with zigzag curve folds. So in the traditional origami design, paper are usually folded along straight edges without stretching, tearing, or cutting. However, a flat sheet of material can also be folded around curve creases as shown in this figure. The folded surface can be isometric mapping onto a 2D domain. The most influential early work on the design of curve crease surfaces was done by David Hoffman. He discovered the geometry properties of curve folding and creates examples of curved folding models as shown here. And using the basic theoretical insights, Eric Demain and June Martina create the artwork for design of origami with curve creases. And Professor June Martina even had a book called Curved Folding Origami Design. So there are some pretty examples as shown here. So for research, Killian and his colleague used developable quad mesh for digital reconstruction of general curved crease surfaces. And the recent work of Rabinovich used the discrete net or orthogonal geodesics to model developable surfaces and curve folds. And here is an application of curved crease origami for face sheet design. So here, these are the two curve folds, and this is the 3D folded shape. So in this project, our contribution is designing methods for such kind of curve pleated structure. So we also want to approximate a given shape with such kind of pleated structure. We introduce the concept of principal pleated structure. So first, we model our curve pleated structure by special PQ mesh. And PQ mesh or planar quadrilateral mesh have been widely used in freeform architecture design. So here is one example, a shopping mall in Australia covered by planar quadrilateral panels. So PQ mesh with nearly rectangular panels follow principal curvature lines of our reference surfaces. So one special kind of such principal mesh is the so-called conic mesh. A pico mesh is conic if each vertex, for each vertex, the incident faces planes are tangent to a right circular cone. So for conic mesh, the sum of the opposite angles are equal at each vertex. The formulation is shown here. And curve-pleated structure is also a kind of developer surfaces. The basic type of the developer surfaces has been introduced before. Okay, so for the modeling of developer surfaces, it's natural to consider the developer surfaces as strip of planar quads. So the PQ strips can be unfolded on the plane. And furthermore, the refinement of PQ strips by subdivision, and we keep the quads planar, can produce a smooth developer surface in the limit. So if we refinement the PQ strips in one direction, we can create the developer strip model. So in general, if we unfolded the strip of these developer strip models to a 2D plane, there are some gaps or overlaps between the unfolded strips. So our curve-pleated structure is a special developer strip model, so which can unfold it without gap. So this video showed examples of a curve-pleated structure isometrically deformed from 3D to 2D. Okay. The most important properties of a curve fold is that the osculating plane bisects the tangent plane beside. So here, if we find a point on this curve creases, and the red one is the osculating plane passing through this point, and these two original plane are the tangent plane passing through on either side, passing through this point, and the angle between the osculating plane and these two original tangent plane should be the same. This is the geometric property of curve folds. So a very special curve-pleated structure as a principal pleated structure. So they have a constant folding angles around each vertex, and they can also isometrically form onto a 2D plane. And during the deformation, the property of constant angle is always true. And this is the principal pleated structure. So for the discrete case, a discrete pleated structure is modeled as a PQ mesh in our setting. So here M is the pleated structure in 3D, and M bar is corresponding isometric mapping on the 2D plane. So the developability constraint of the pleated structures require the sum of the angles around each vertex to be 2 pi. And then for the discrete principal pleated structure, we model it as a special conic mesh. So it has the property of conic mesh, and also it has the developability constraint. So we can get the conclusion that the sum of the opposite angles should be pi for all the vertices. This is the constraint for principal pleated structure. So the principal pleated structure has constant folding angles, and its offset is still a principal pleated structure because the properties of conical mesh. Okay, so these are some examples of principal pleated structure, and this wood structure is also a random result of a principal pleated structure, which can be folded from a 2D structure. So if we look at the detail, we can find out the thickness of this the structure is constant. This is a property of a conical mesh. And the property of principal pleated structure can also imply that is a flexible mechanism. So this is a real model of a principal pleated structure we built. And the video shows that the deformation from a 2D shape to the 3D shape. Okay. So to design such kind of pleated structure, we introduced the concept of pseudogeodesics. So a pseudogeodesics is a surface curve whose oscillating plane form a constant angle with the surfaces. So here, as shown here, this the blue curve is a pseudogeodesics. For each point at this curve, there we can compute the oscillating plane, this blue plane, and also for this point, there is a tangent plane of the reference surfaces. And the angle between these two planes is constant for the pseudogeodesics. So for example, this is the case for the constant angle equal pi/6. There are two special kinds of pseudogeodesics. One is asymptotic curves where the constant angle equal 0, and also another case is geodesics where the constant angle equal pi/2. Okay, so the whole computation pipeline including two major parts. One is the initialization part, and another is optimization part. So we initial the pleated structure based on the concept of pseudogeodesics. So here, this blue dots are actually some pseudogeodesic curves. So we can imagine that we see these curves around the direction of tangent direction. So these red lines are the oscillating plane. And we do the initialization by offset the pseudogeodesics up and down, and connect those pseudogeodesics. So here we can assume that after the offset, the oscillating plane are approximately the same as the original one. So then the oscillating plane can form a constant angle with the two tangent plane besides. So this is exactly the geometry constraint of curve fold. So if we do the initialization in this way, the initialization is good because it satisfies the geometry property of curve folds. So here is another case for the constant angle theta equal pi/6. This is the oscillating plane, and this is the tangent plane. And the angles are the same between the oscillating plane and the two tangent plane besides. Okay, so the initialization based on pseudogeodesics can be applied in two ways. So one is for a given reference surface, we first compute the evolution of surfaces, and using this and those curves are considered as pseudogeodesics. Another way is that we compute a family of nearly equidistant pseudogeodesics on a given reference surfaces. So here we introduce the first one. This is a given curve. We can first compute its normal, tangent, and binormal direction. So our goal is to get an evolution surface such that these curves are approximately the pseudogeodesics. So the evolutionary direction is shown in this form. So here we show two different cases. One is the constant angle equal 0, and another is constant angle equal pi/6. And we do the evolution again, get the evolutionary surfaces. And those polylines are actually approximately the pseudogeodesics. And then we can do the offset, as we introduced before, to get the initialization of those curve-pleated structures. Okay, so another initialization is for a given reference surface. We can prescribe a guiding curve. So around this guiding curve, we can sample some vortices as a starting point, and we trace these pseudogeodesics and we do the offsets and get the initialization of curve folding structure. And here, to emphasize the importance of initialization, we show example of bad initialization for the same surfaces. So here we generate the initialization based on a random given quad mesh. So for this input, if we want to optimize the quads to be planar, we can find out that the shape will be far away from the reference surface. But if we keep the closeness term, and then the planarity of the face will be bad. So here the red means the face, the quads are not planar. Okay, so the further numerical optimization, so we use those, so in the optimization, so we formulate the constraint or the constraint as energy terms. So the planarity is represented by the orthogonality of the normal and its corresponding edges. So here is for these 7 guns, but actually we only optimize for quad mesh. Okay. So durability is guaranteed by forcing each face of the 3D quads and its 2D counterpart has the same edge length and also the same length of diagonals. So we also require the vortices to close to the initial creases and also the fairness term. And for the principal pleated structure, has one more constraint, requires folding angle to be constant. Okay. And in the end, we combine all the energy term as object function and solve the optimization problem with LM methods. So here we show an optimized curve pleated structure around a node curve, and the right one is physics model. So these two examples show the results of non-uniform evolution. So it means that the moving speed of the curves for the polylines are not the same. So here the size are bigger than here. Okay. So we also get some result to complete structure to approximate giving reference surfaces. This is 2D unfolding and the physical models. Okay. So for approximate a given reference, we can also use different guiding curve to do the initialization of curve pleated structure. So here we show examples. We use 2 different curve pleated structure to approximate the same reference surfaces. Okay. The second project is freeform quad-based karigami. So karigami, as we mentioned before, is a variation of origami. So besides folding, it can be also cut and folded. can be cutting is also allowed, and also even some holes are allowed. So pop-up structure is the famous example of Karigami. So here are two more such kind of pop-up structure. So for the research on pop-up structure, Professor Shiming Hu and his team has a publication of figure 2010 on it. So in our project, we will focus on another type of Karigami. So these are two examples of folded box. So for a general case, here is a motion for set from an open state to on plane to a closed box shape. So here is a previous work on the design of such kind of box-like Karigami. So, but they can only handle the regular case. This means that the 2D pattern and also the 3D boxes are regular. They can only use such kind of structure to approximate planes. So then what we want to do is to extend the approximation to extend the approximation to reference surfaces, to freeform surfaces. So here is one example. The closed box is used to approximate a given 3D freeform surface, and the structure can be flattened onto a 2D plane with holes. There are three types of box structure we worked on in this project. So this one we call it box Karigami, or type B for short. So here for each face there is a box. And this one, the second one, we call it checkerboard box Karigami, or type CB for short. So here we can see the difference, and the box are distributed alternatively like a checkerboard. So only one half of the face have box, another half is covered with planar faces. And the third type, we call it checkerboard Karigami, type C for short. The difference with the previous one is that the neighboring box are required to share the same axis. Okay. So if we compare these three types, we can find out they have different holes on 2D. So for type B, the hole is a 8-side hole. The holes are 8-side holes. So here the colors, the same color means the edge has the same edge length. So for 8-side holes, there are 4 pairs of equal edge lengths. And for type CB, the holes are cage shapes, and it has 2 pairs of equal edge lengths. And type C has the strongest constraint. The holes on the 2D are rhombuses whose edges have the same edge length. So the goal of our algorithm is for a given reference surfaces to generate a box-like structure to cover its face, and the box structure can be flattened onto the plane such that the structure can be constructed by cutting and folding a flat sheet of materials. Okay, the essential part of the project is the discrete expanding mapping. So this mapping is not a traditional one, such as conformal or isometric mapping. So as shown in this figure, we call the mesh connected by these red dots as a base mesh. So here the base mesh for the closed state is BM, and the base mesh for the open state is a BM bar. The mapping from BM to BM bar is a kind of expansion. This mapping requires the principal distortion always be greater than 1. So for a given 3D shape, we map the shape on 2D with the proper distortion control. And after the distortion has been computed, we can then design the height and the inclining angles of the boxes as initial for further numerical optimization. So here I will not introduce the details of the algorithm for designing the heights and inclining angles. So we show some example results with the box carigami design. So for complex shapes, we have to cut it for mapping. So for example, here for this leaning tower model, we map it with 4 cars, and for this model, we have to cut it into 2 pieces with disk topology and approximate the whole shape with 2 pieces of flat materials. To validate our algorithm and design, we also show here some real paper models. Okay, so we also made some models with other materials such as this one. So one side is wood and another side is a feather-like material. So this is a 3x3 models, although simple, but if we consider this 3x3 as a basic element, this element can actually be repeat and rotate 90 degrees and connect them to form a bigger structure, which could be used as a roof design. So another work I think is quite interesting is the curved carigami. So similar as curved origami, the cutting lines are not straight. So as far as I know, there is almost no such kind of design before. So what we did is using the idea of subdivision. So because we can get the box-like carigami first, it could be used as a good initialization. And then based on this shape, we subdivide the 3D, both 3D and 2D quad mesh to get some initialization. And then we use it as initial to compute the curved carigami design. So these are the real fabrication of the curved carigami. Okay, the third project is called shape morphing mechanical metamaterials. So I consider this work also as a carigami related research. So a typical feature of metamaterial is their aesthetic behavior. So as shown here, this is example of aesthetic structure is a physical model we made with planar sheet of materials. So the model has 2 states, closed states in 2D and open state in 3D. So one goal of our work is to design the cutting lines in 2D such that the open state can approximate certain given reference shape. An inverse problem is that the open state is in 2D and the closed state in 3D. So here is also a physical model we built for such a purpose. So more general goal is that open state and the closed state are both in 3D. So there are some previous work on aesthetic structures, such as this one by Professor Makpoli and his team. They use the triangle mesh for the aesthetic design, and they compute the initialization using conformal mapping. And this is another work used quad mesh as its basic designing element to publish in Natural Materials. This is a 2D design where the closed state is a square and its open state is a circle. And these are the results used to approximate 3D shapes. If we look at the results, we can find out that the fairness of these results is not good. So for the design of quad mesh, quad-based metamaterials, we propose a new mapping called constant mean stretching. So here I will explain this concept. So this is a 2x2 regular quartz in closed state. The red dots are the barycenter of this quartz. And the length and width of every quartz are A and B, and the quartz connected by the barycenter has the same length and width. So when the structure opens extremely, we can do the same thing by connecting the barycenters. So here the quartz is a square with edge length W. Okay, so it's not difficult to find the relation between A, B, and W. So here is their the relations. So we can define the stretch or the vertical direction as lambda 1, and also the stretch on the horizontal direction as lambda 2. And then we will get to conclude the equation that the sum of these two stretch, or the average, the mean value of this stretch is a constant value. So this is the constraint we used in design of the structure deformed from closed to open state. So here is an example. The left one is a reference surface for the closed state, and the right one is a reference surface for the open state. So our goal is to design a structure whose closed states approximate this surface and its open state approximate another one. So the two in between are the initial grades, which satisfy the constraint of constant mean stretch. So we first map these grades onto the reference surfaces. So here there are three types of meshes. The blue one are the grids, the red one are the control mesh, and the yellow one are the oscillating structures. We actually compute the whole the constant mean stretching constraint use the control mesh, the red one. So the stretch can be defined by the ratio of the corresponding diagonals of the corresponding faces of control mesh. So we first optimize the control mesh to satisfy the constant mean stretching constraint, and then derive an initial structure of the oscillatics, and finally optimize the oscillator structures with a numerical optimization method, as we introduced before, like LM methods. So here are some examples. So for this one, this is the closed state is in 2D, and the open state is in 3D to approximate a negative curvature surfaces. And this is another case. So here the 2D, the open state is in 2D and the closed state is in 3D. Another case. Here both the closed and the open state are in 3D. Okay, so this is to approximate the Leaning Tower. The closed state is in 2D. And we can also compute a structure that to approximate this shape that the closed state is in 3D. Okay, so here I show the oscillatic structure expanded from closed quad mesh on sphere. So different closed mesh have different opening oscillatics. So another part of this project is a bistable oscillatics. Okay, so here in this video, we can find out the structure has two stable states, open and closed. So here you can find the structure are regular, and the underlying patterns are either regular quads or regular triangles. So the purest work on bistable structure can only handle such kind of regular repetitive patterns. Okay, so here is a figure show the basic element of bistable aesthetics. The left one is a closed states, the right one is in the open state. If we look at the two different colors, the yellow one has a rotation and the blue one only has a translation. So here we show the relation between these two stretch on horizontal and also vertical direction. Between these two stretch and the internal design of these chords, such as its width, length, and also the angles of these chords. So in the initialization of the bistable aesthetics, we use the relation of those geometry properties. So, but I will not explain the details here. So in our project, we extend the purest work on regular design to some general design. Here some, for the 2D case, this is in the design in closed state and is open state. This is the physical model. Another example, closed state, open state, closed and open state. So we also try to design 3D bistable structure. So in the design of 3D bistable structure, the direction of the rotational axis are the essential parameters. Okay, so here, if we look at the two patterns, they are quite similar. And the difference is their rotational axis on the thickness directions. So for these two examples, we also build physical models. Here you can find the animation. So the left one is for the positive curvature surfaces, and the right one is for the negative curvature surfaces. And these are the physical models. So for the future work, we would like to explore more ways to design patterns of pseudo geodesics for the initialization of curve-pleated structure. We are also interested in the reconstruction with curve flows that are not pleated structures. We also would like to investigate the multi-stable aesthetic structures. And that's it. Thank you very much.
Okay, thank you, Caigui, for the very nice talk. So yeah, I mean, it's amazing that we can build a very nice freeform surface from a piece of flat material. So yeah, so and with lots of nice examples in your presentation. So actually, I have one question for Caigui. Caigui, can you turn on your camera so we can see you? Okay. So my question is, so you introduced 3 projects, right? So the second one is about Karigami, and the third one is about Auxetic. So that looks quite similar, right? So can you tell us what is the essential difference between these two kinds of structures? Is that because of joining? Because if you look at the Auxetic, they can rotate, right? I mean, around. So what is
I mean, the second project is actually is a very special Karigami structure. We call it a box-like Karigami. Mm-hmm. So it's quite different. I mean, they have 3 types of such kind of. We defined 3 types of such kind of designs. Yeah, but I mean the last one, the metamaterials has more degree freedom for design.
So that's the keyword, right? The degree of freedom, right? So for Auxetic, they have more. More freedom.
Yeah.
Yeah, because it looks quite similar because both of them have holes inside, right?
Yes. I mean, this is kind of an extension of Karigami, So usually we talk about carigami, maybe we don't require the shape have some holes. Yeah.
Okay, I have one more question for you. So if you look at the results in a curved fold structure, so it's very nice. And also you do some fabrication, right? And we know when you fabricate, it's actually basically fabricated in a flat state.
Yes.
And
yes.
if there are holes, of course we can use this cut to count these holes, right? So what I'm wondering is how you fold them. Because to me, I mean, I don't know whether the machine can help you to fold them automatically, or I mean, how do you do that?
You mean how do I cut the holes?
Not cut holes. I mean, after you cut the holes, you need to do the curved folding, right?
Yes.
My question is how did you do this curved folding? Are you using some machines or?
I think this result are by hand, I think.
Oh, it's by hand. It's manually.
Yeah.
Okay. Yeah. But you need to do some markers on the flat sheet, right?
Yes, that's true.
Okay, I see. Okay, maybe maybe in the future we can have some machines to do that. Now we can do it more precise, right?
Yes, that's true.
Okay.
Also, I think there are some deformations, which is maybe there's some deformation which is not easy to control.
Okay, yeah, that's true. Okay, I have one question for Nico. So Nico, are you here?
Yes, of course.
Okay. Yeah. So I mean, I learned a lot from your motivational talk, and if you look at I mean these works, right? So my understanding is that I mean a lot of this work in architectural geometry, they are more focused on the design. So the focus on the design of free-form surface with lots of good properties. So my question is, do you think there are some research opportunities to focus on, I mean, the fabrication? Because once you do design, eventually you need to do the fabrication and the assembly, construction, all these kind of things, right?
Yeah, good point. I think there was a paper from Philip Bloch, Daniele Panozzo that started like working like a few years ago on like how you can assemble masonry structure. And yeah, I think assembly is still a very unexplored field. I mean, I think it would be interesting. Suppose you have to assemble a grid shell, right? Suppose you have a certain amount of cranes and you have a certain amount of cranes or constraints. So how you can derive the right sequence of assembling, right, such that you utilize as much as possible, or you move as less as possible. Sorry, your equipment at the same time you keep the structure as stable as possible. That's for example a good question, and I haven't seen not so many works in this direction. But assembly, it's a very big topics. You can think also like if you think about tensegrity. Assembling that tensorities was a nightmare, right? So and it's very challenging. I think it's a lot, the space of solution is huge, right? And it's very interesting. And I think it's most of the part of the construction of the cost of construction this big surface. It's deriving like it's workload, right? It's basically workload. How you can make and use your resources as cheap as possible, I think will make a dramatic impact on the industry. So at the same time, if you see also these nice origami shapes, right? I mean, this is also a way to manufacture, to fabricate nice curved surface, right? And if you want to scale it up to bigger surface, maybe you can actually, instead of using the hands, you can embed some cables, right? And actuate them through cables, for example, some kind of mechanism. So there is still a lot of room for research. I think it will be a very, very good direction with respect to, yes, classical like optimization of, which is also important, right? But optimization of geometric properties, like also assembling. I think it's still not enough explored in my experience.
Yeah. Okay. Yes. Yes. I think that's a very good answer to my question. Okay, so I have one more question for Nico. Yeah, so you introduced two kinds of very interesting structure, right? One is tensegrity, the other one is grid shell. And when you design these two kinds of structures, you are actually interested about the structure stability, right?
Yeah.
So my question is, when you analyze the structure stability, do you have any assumption about the external forces? Because when you talk about stability, it's relevant to the external forces, right?
Right. So there are two different scenarios, right? For example, in grid shell, what we do to measure stability and to assess that our structure is stable is we actually imagine to have, for example, some snow on the top, uniformly distributed. Basically, you distribute the forces given the Voronoi areas of each vertex, right? And then we actually increase. So for this grid shell, usually what you do in engineering, and we used one of the methods to assess the final stability, is to find the buckling multiplier, which is how much you can multiply the weight of the structure itself until it actually collapses.
Okay.
So it's like imagine to have some snow over the surface, right? And you increase the level of the snow. So this multiply, when you see 2.4 in the slides, like the structure supports 2.5 times its own weight, which is good, right? But it's also difficult to model and to simulate it. You need to have specialized like FEM package because buckling is very nonlinear. On the other hand, for tensegrity, it was a bit different. So tensegrity, you want, so coming to your question, for boundary constraints in terms of grid shell, usually you have gravity, you have just one direction, right? The gravity load, and you increment until it collapses. So in tensegrity, the difference is like we actually look into in a tensegrity that there is no any mechanism. So with mechanism, I intend any possible like you cannot make any rotation, you cannot rotate any parts to make the tensegrity fall down. There is no rigid rotation for any piece of the tensegrity that can change its shape. So every time you try to rotate one object or a set of objects or any kind of combination of objects together, it's impossible. So it means like either you put a cable in tension or a truss in compression. So then it's like independent by the orientation. So I think that tensegrity is very rigid, right? You can push in every direction, and we check that there is no mechanism, that there is no way with your hands that any kind of grabbing combination you can disassemble. It's called mechanism.
Yes. Okay. I think there's no further questions from me so I think that's all for today's talk, and thank you for both speakers for a very nice talk. And so that's all for today's talk. Thank you.
Thank you.